When we look out at the ocean, we only see the surface, a fateful misconception, because what hides within the abyssal depths turns our entire understanding of life upside down. There we encounter the fascinating phenomenon of deep-sea gigantism. In a world completely devoid of light, certain creatures evolve into true giants, like a sea spider effortlessly towering over a golden retriever, or jellyfish drifting silently past, with tentacles reaching the size of a whale. All of them defy the crushing, lethal pressure. Even the most inconspicuous inhabitants of the sea have grown to unimaginable proportions here. All of these deep-sea creatures are absolutely real, here in the oldest and deepest oceans of our planet. In places more alien to us than any fictional planet, where the rules of known biologies no longer apply. It is a hidden mystery of evolution that occurs only in the most extreme depths of our oceans. There, where freezing cold, eternal darkness, and crushing pressure reign, conditions that defy all biological logic, because instead of wasting away, life here mutates to monumental proportions. Shrimp reach sizes longer than your own forearm, and crabs spread their legs wider than a human is tall. Why do they defy the laws of our world? But what secret lies behind this strategy? Why does evolution push life to such extremes in an environment so seemingly hostile? Is deep-sea gigantism a mere whim of nature, or the ultimate tool for survival? The answer lies in the deep. Join us on a journey away from the sunlit epipelagic zone, the familiar roof of the ocean, and down into an untouched realm. Up here, the water is warm, fish shimmer in every color, and the energy of the sun drives the endless engine of photosynthesis. But the moment we cross the 200-meter mark, everything changes. We enter the mesopelagic zone, the twilight zone of the ocean. With every meter, the light loses its power. Colors fade into a monotonous gray, and the familiar warmth of everyday life quickly vanishes. Below the magical boundary of 1,000 meters, the sun finally loses its power. Welcome to the bathypelagic zone, the midnight zone of our planet. In this world of eternal darkness, the only light is the biological glow of the creatures themselves. A ghostly dance of bioluminescence. A biological glow generated by the creatures themselves to lure prey or find a mate. Welcome to the Terralog's deep-sea journey. If this descent into the unexplored abysses of our planet fascinates you as much as it does us, please leave a thumbs up. It helps us bring these hidden stories to the surface. Because right down here, in this absolute pitch-black darkness, the transformation begins. The pressure down here is monumental, hundreds of times higher than in our familiar world at the surface. Let us try a thought experiment. Imagine the immense weight of a fully loaded delivery van pressing down on every single square centimeter of your body. That is the reality at these depths. For us humans, this would mean a fraction of a second until absolute, certain death. Our lungs would instantly collapse, and every hollow space inside our bodies would mercilessly implode. Yet for the inhabitants of these abyssal depths, this monumental pressure is no obstacle. It is a constant, as natural and invisible as the air we need to breathe. And right here lies the paradox of evolution. This extreme pressure does not seem to prevent gigantic body sizes, but rather favors them. In smaller animals, the ratio of surface area to body volume is much larger. This means that the crushing pressure can attack their cellular structures far more intensely and directly. Down here, gigantic size is not a luxury. It is a protective shield. A more massive body with greater internal volume relative to its surface area offers far higher physical stability. Its internal structures remain perfectly intact, even under this immense crushing load. Let us take a closer look at one of the most fascinating and prominent representatives of this phenomenon, the Japanese spider crab. While the small shore crabs you might know from the North Sea mudflats fit comfortably into the palm of a child's hand, this giant plays in a completely different league. With a leg span of nearly 4 meters, It is the largest living arthropod on our planet. If this creature were standing in your own living room, its legs would literally reach from one wall to the other. It moves agonizingly slow, almost mechanically, like an ancient relic from a long-forgotten era, silently stalking across the ocean floor. Its actual body seems almost tiny compared to its grotesquely long limbs, yet it is precisely this immense reach that gives it an evolutionary advantage in the absolute darkness. Because in the depths of the ocean, size is not merely a whim of nature. It is not a privilege, but often a matter of pure, naked survival. This brings us to the most fundamental challenge of life in the deep: hunger. The deep sea is an endless, black desert. Since not a single green leaf can grow down here, the very foundation of the food chain as we know it is completely missing. All life in this darkness is unconditionally dependent on what falls from the upper layers. Scientists call this phenomenon, almost poetically, marine snow. It is a constant, silent drizzle of dead plankton, microscopic waste, and the decaying remains of marine life, slowly sinking from the sunlit zones into the abyss. Imagine it as if you had to survive exclusively on the dust, drifting down from the ceiling of a gigantic cathedral. It is vanishingly scarce, extremely nutrient-poor, and the competition in the darkness is absolutely merciless. Right here, a biological law comes into play that sounds completely paradoxical at first. To survive on extremely little food, you have to become gigantically large. A more massive body operates fundamentally more efficiently. In science, this principle is known as Kleiber's law. A small animal like a mouse possesses a racing, relentless metabolism. It is a slave to its own body, and must eat continuously just to keep from starving to death within a matter of hours. A large animal, like an elephant on land or a giant isopod on the ocean floor, burns astonishingly little energy relative to its mass. In the freezing cold of the deep sea, where temperatures often hover just above freezing, the body's chemical reactions slow down even further. A giant of the deep is essentially like a perfectly insulated passive house. It stores and conserves its precious energy over immense periods of time. When a giant isopod, scientifically known as Bathynomus giganteus, finally encounters a real meal, like a dead fish that has made the long journey into the abyss, there is no holding back. It gorges itself so incredibly full that it loses almost all ability to move. But this radical feast is a calculated strategy. This single cache of energy lasts for months, sometimes even years. In laboratory experiments, these fascinating creatures survived for over 5 years without a single bite of food. A smaller animal, with minimal storage capacity and a relentlessly fast metabolism, would have starved to death in this wasteland long ago. Down here, gigantic size is not a luxury. It is the ultimate life insurance policy against an eternal famine. This phenomenon is further driven by Bergmann's rule, which states that animals, in freezing environments, evolutionarily tend to develop far larger bodies than their close relatives in warm regions of the world. Although this rule was originally defined for warm-blooded animals like penguins or polar bears, we observe a strikingly similar pattern among the invertebrates of the deep sea. Freezing water slows down cellular processes. A tiny, fragile organism is left defenseless against the cold, whereas a massive, compact body possesses immense thermal and physiological stability, even when the creature is cold-blooded. But it is not just the freezing cold or the gnawing hunger. It is pure, naked fear. In the endless expanses of the deep sea, there are no hiding places. There are no protective coral reefs, no safe crevices for a tiny shrimp to dart into when danger looms. The ocean floor is a merciless, open plain of mud and darkness. In this arena, a brutal law rings true. To be small is to be a defenseless snack. To be large is to be an impregnable fortress. With its massive, segmented, chitinous armor, the giant isopod resembles a heavily armed knight of the deep, simply invincible to most predators. Its sheer mass is its greatest weapon, pure deterrence. Even a lurking anglerfish will think twice before opening its jaws to swallow a living, football-sized tank. The risk of choking to death on this prey is simply too high. In a world without cover, your own body becomes the ultimate bastion. These creatures are not monsters lurking to drag ships into the abyss, as ancient mariner legends suggest. They are our planet's ultimate survivors, shaped over millions of years by the most extreme forces of nature. Their strategies for survival are as alien as their appearance. They grow in extreme slow motion, they live for nearly an eternity, and they possess a patience that is utterly incomprehensible to us humans, who restlessly think in mere seconds and minutes. While we up here rush from moment to moment in our hectic, noisy world, they remain suspended in that timeless darkness, and wait. Waiting for the next silent flake of marine snow, waiting for the next rare opportunity. We have now taken our first deep look at the fundamental laws of this realm. Laws dictated by four merciless forces: monumental pressure, freezing cold, extreme scarcity, and the absolute perfection of efficiency. But the deep sea hides creatures of an entirely different caliber. Beings that have long outgrown the word large to attain truly titanic proportions. Creatures with eyes the size of basketballs, perfectly engineered to capture even the faintest, most microscopic glimmers of light in the infinite darkness. While the giant isopod is the unyielding tank of the ocean floor, another giant glides silently through the open, bottomless void, shattering the boundaries of human imagination. When we think of the ancient myths of the high seas, one specific terrifying image invariably surfaces in our minds: the kraken. A legendary monster of the deep that wraps its massive tentacles around mighty ships, dragging them into the abyss as if they were mere toy boats in a bathtub. These tales are centuries old, steeped in myth, and vastly exaggerated, yet they spring from a real dark truth. Because down there, in the eternal black, creatures actually lurk that once brought these legends to life. But the reality of the deep sea is more fascinating, more alien, and far more complex than any sailor's yarn. Let us pull back the curtains of science and pit two of the most titanic and mysterious rulers of this realm directly against each other: the giant squid and the colossal squid. Many people lump these two giants together or mistake them for the exact same animal, a fatal error. Because the anatomical difference between them is about as fundamental as that between a graceful basketball player and a massive sumo wrestler. Both are titans of the sea, yet they were engineered for entirely different survival strategies in the extreme deep. The most legendary and renowned representative of these titanic cephalopods is the giant squid. He is the undisputed icon of cryptozoology, the beast that Jules Verne immortalized in his masterpiece, 20,000 Leagues Under the Sea. For centuries, humanity knew absolutely nothing about this creature, except for what the silent carcasses washed up on desolate beaches chose to reveal. A ghost of the oceans, completely hidden from human eyes. It wasn't until 2004 that scientists achieved the impossible. The world's first photographs of a living giant squid in its natural habitat. Captured in the eternal twilight zone, nearly 1,000 meters beneath the ocean surface, and the data we have gathered since is breathtaking. The largest verified specimen ever found measured a staggering 13 meters. To put that into perspective, that is exactly the length of a standard city transit bus. The vast majority of this enormous length is made up of its two extremely long feeding tentacles, which it launches like elastic whips toward its prey. While the giant squid is incredibly long, it is a surprising lightweight. A full-grown specimen weighs just 250 kilograms, making it the lean, wiry sprinter of the deep sea. But when we leave the temperate zones behind and venture deep into the freezing, merciless waters of the Southern Ocean surrounding Antarctica, we encounter the true heavyweight champion of the invertebrates, the colossal squid. Contrary to what its monumental name suggests, The colossal squid is often slightly shorter than the giant squid, usually reaching only about 10 meters in length. But do not let the missing meters fool you. What it lacks in length, it more than makes up for in sheer brute mass. While the giant squid is sleek and wire-thin, the colossal squid is inherently massive, compact, and built like an absolute tank. A single one of these colossi can tip the scales at an astonishing 500 to 700 kilograms. To put that into perspective, imagine taking a tiny Honda Fit or one of those little Chevy Sparks, those small city cars you see everywhere in American downtowns, and compressing all of that weight into the body of a deep-sea squid. That's the kind of crazy mass we're talking about. The colossal squid is the heaviest invertebrate on the entire planet. It lives in waters well over 2,000 meters deep, a realm that's even darker, colder, and more brutal than the giant squid's territory. So why in the world did evolution make it so massively bigger? The answer lies in an absolutely unique evolutionary masterstroke. The colossal squid is one of the rarest examples of a phenomenon known as double overlapping gigantism. This means the creature benefits from two massive growth effects simultaneously. First, deep-sea gigantism, which drives creatures in the extreme depths to scale up, and second, polar gigantism, which molds life in freezing polar regions into true giants. In the colossal squid, these two evolutionary superpowers fuse into a single titanic force. He essentially hit the absolute jackpot in the genetic lottery, or, depending on your perspective, drew the ticket to the most extreme survival conditions on Earth. The habitat of the colossal squid around Antarctica is a realm of absolute superlatives. Down here, water temperatures frequently drop well below the standard freezing point. The ocean only remains fluid in these depths because its immense salinity and monstrous pressure prevent the water from turning to ice. In this freezing, hostile environment, the colossal squid has undergone a radical adaptation. Biologically, it belongs to the glass squid family, creatures that, as their name implies, are usually completely transparent to blend into the water. But at this immense size and extreme cold, transparency is no longer an evolutionary option. Instead, it features a thick, deep reddish skin. But why red, of all colors? The answer is a stroke of physics genius. In the depths of the ocean, red light is the very first to be absorbed. A red creature in the deep sea does not appear red at all, but pitch black. It is the perfect, natural stealth cloak. However, this thick, rugged skin doesn't just provide visual cover. It acts as a structural shield, protecting its massive body from the merciless forces of the environment. The colossal squid is a perfectly armored tank, drifting silently through the frozen sea. Yet, the truly terrifying thing about these creatures is not their sheer mass, it is their weaponry. While the giant squid grips its prey with suckers lined with tiny, serrated chitinous teeth, the colossal squid takes things to a whole new level. In the colossal squid, however, evolution has dialed the lethality up a notch. Its tentacles are armed with swiveling, razor-sharp chitinous hooks that rotate independently. When this predator strikes its prey, such as the massive Antarctic toothfish, these biological meat hooks gouge deep into the flesh, tearing devastating wounds. Escape from this deadly embrace is utterly impossible. It is easy, given this description, to paint the picture of a restless, aggressive monster patrolling the oceans, tearing apart everything in its path. But, at this point, we must dismantle a profound misconception deeply embedded in our human psyche. We instinctively tend to equate monumental size and lethal weaponry with permanent aggression and dominance. The reality of the deep sea, however, follows an entirely different script. In the deep sea, the exact opposite is true, because with this monumental size comes a steep evolutionary price, an extremely sluggish metabolism. Think of it as the ultimate virtue of thriftiness, one that the colossal squid has mastered to absolute perfection. It operates under a fundamental biological principle that scientists refer to as Kleiber's law. This law dictates that an organism's metabolic rate does not scale linearly with its body size. A creature that is 1,000 times heavier than another does not require 1,000 times more energy. Instead, as an animal grows more massive, its energy consumption per kilogram of body mass becomes increasingly efficient. It is nature's ultimate energy-saving discount, and the colossal squid pushes this principle to the absolute limit. Scientific calculations reveal a phenomenon that is nothing short of absurd. The metabolic demand of the colossal squid is so heavily throttled that a single kilogram of its body tissue requires a mere 45 calories per day. Relative to its muscle mass, that is less energy than you would find in half an apple or a single small cookie. By comparison, a single gram of human tissue burns a vast multiple of that just to keep us alive. The colossal squid is a biomechanical masterpiece of absolute energy minimization. In plain terms, this means this 700-kilogram titan is no wild, restless predator chasing its prey through the oceans in epic pursuits. It simply cannot afford to waste precious energy on a sprint. The colossal squid is a master of absolute passivity, an ambush predator. It hangs nearly motionless in the pitch-black water for hours, waiting. It waits patiently for prey to unwittingly swim directly into the strike zone of its lethal hooks. A single, large toothfish provides this giant with enough energy to sustain it for nearly 200 days. For us humans, that would be the equivalent of sitting down for one single, hearty Sunday roast, and then not having to eat another single bite until the following summer. That is the hyper-efficient, almost meditative life of the colossal squid. Yet, to successfully execute this radical strategy of sitting and waiting in absolute blackness, evolution has gifted it with yet another unparalleled superlative: the largest eyes in the entire animal kingdom. Its eyes can reach a diameter of up to 30 centimeters. This means that a single eye of this deep-sea monster is literally the size of a regulation soccer ball. A soccer ball is actually smaller than the eye of this titan. It is no exaggeration to say that its eye is the size of an entire human head. But why does a creature need such gargantuan visual organs in the absolute blackness of the deep sea? The answer is surprising. Not primarily to find prey, but to avoid becoming prey itself. Because despite its brute mass and rotating hooks, the colossal squid has one ultimate natural arch-nemesis: the sperm whale. Sperm whales are the only creatures on this planet that dare to hunt a full-grown colossal squid in its own domain. And this is exactly where the superpower of those gargantuan eyes comes into play. They are evolutionary radar systems designed to detect the faintest glimmer of bioluminescence. As the massive whale plows through the darkness, it inevitably disturbs tiny deep-sea organisms that light up like a security alarm upon contact. The squid's eye registers the glowing silhouette of the approaching hunter long before the whale even knows it's there. This phenomenon occurs when a massive body like that of the sperm whale glides through the darkness, disturbing countless microscopic plankton in its path. It functions as a cosmic early warning system. The colossal squid detects the faint bioluminescent shimmer created by the approaching whale long before the mammal's sophisticated sonar can locate it. Yet the bodies of these hunters reveal that escape is not always successful. Sperm whales frequently bear deep, lasting scars, perfectly circular sucker marks and long, jagged gashes left by the colossal squid's razor-sharp hooks. In the past, we believed these were the marks of epic battles where the squid actively attacked the whale. Today, science knows they are purely defensive wounds. The squid does not fight for dominance or territory. It fights desperately for its bare survival, trying to escape the whale's lethal jaws. These creatures are not malevolent monsters of the deep. They are masterpieces of evolutionary efficiency. They have learned to survive with absolute, radical minimalism in a world that does not forgive a single mistake. Their monumental size is not a sign of evolutionary abundance, but a radical adaptation to permanent scarcity. They are gigantic, silently drifting energy-saving lamps in the eternal darkness of the ocean. But how exactly does this extremely slowed-down metabolism function physiologically? How does a creature manage to run such a massive body on a virtually non-existent amount of energy without simply starving or freezing to death in this icy hell? And why does the cold play such a decisive role that it drives these creatures to such extreme proportions in the first place? This leads us deeper into the biochemical secrets of the deep, to a realm where energy is the most precious resource in the universe. Just 45 calories a day for a 700-kilogram titan. Let that number sink in for a moment. Energetically speaking, that's like driving a 40-ton semi-truck all the way from New York to Los Angeles while consuming only a single shot glass of diesel. It completely contradicts everything we think we know about energy consumption. When we exercise, when we work, or when we simply exist, we humans burn calories like a raging blast furnace. So how do these creatures manage to seemingly defy the laws of thermodynamics? The answer lies not in magic, but in pure, brutal efficiency. It's a virtue we Americans love to celebrate in our own engineering, yet nature perfected it millions of years before we ever existed. To unlock the secret behind this energy-saving miracle, we have to look at a fundamental law of nature known in biology as Kleiber's law. In the 1930s, the Swiss agricultural scientist Max Kleiber stumbled upon a baffling principle. He proved that an organism's metabolic rate does not scale proportionally with its physical mass. While that might sound like complex physics at first, it can actually be broken down quite simply. If you double the weight of a creature, it does not mean its energy requirement doubles along with it. A horse that weighs 1,000 times more than a tiny mouse doesn't need 1,000 times more fuel to keep its biological engine running. Think of it like the heating efficiency of an apartment block in the city. Heating a small studio apartment is incredibly expensive per square meter because heat rapidly escapes through the outer walls. A massive residential block, on the other hand, retains energy much better and operates on a dramatically more efficient scale. The interior apartments practically insulate one another. Because the total volume is so massive, the relative surface area where heat could actually escape remains incredibly small. This is exactly how large animals function. They are essentially living apartment blocks. The more mass they accumulate, the more economically and efficiently their internal engine runs. Their metabolism scales to the power of 3/4 of their body mass. In plain terms, this means that in a nutrient-poor environment like the deep sea, being massive is the ultimate energy-saving trick. A small organism has to feed constantly, like a nervous stockbroker permanently shouting into a phone. Its internal fire burns incredibly fast and hot. A giant, on the other hand, is the definition of calm itself. It is like a massive ocean liner that builds up momentum once and then glides silently for days without anyone having to shovel a single lump of coal. But Kleiber's law really only explains part of the story. It tells us why enormous size can be so efficient, but it doesn't yet explain why it is an absolute necessity for survival in the icy depths of the ocean. This is where the cold comes into play. We humans are warm-blooded mammals endotherms, and that is a biological luxury that costs us an incredible amount of energy. It doesn't matter if it's 30 degrees in the shade or minus 10 degrees out on a freezing mountain peak. Our bodies work tirelessly to maintain a constant core temperature of 37 degrees Celsius. Energetically speaking, we are like houses that run their heating on full blast all year round while leaving every single window wide open. For a warm-blooded animal, every single additional kilogram of body mass is a massive extra burden on the biological heating bill. This is exactly why polar bears grow powerful, but they will never become as absurdly gigantic as the invertebrates of the deep sea. Eventually, the system hits a wall. They simply cannot hunt enough seals to keep that massive internal furnace running 24/7. The giants of the deep sea, the crabs, the giant isopods, the colossal squids, are ectothermic, meaning they are cold-blooded. They simply possess no internal heating system. At every single moment, their body temperature matches that of the surrounding water exactly. And in the deep sea, that means just above freezing, often between 1 and 4 degrees Celsius. In this extreme cold, something fundamental happens to the very chemistry of life itself. When temperatures drop, chemistry shifts into a lower gear. This applies to a car rusting in winter just as much as it does to the biochemical processes inside a deep-sea organism. In these abyssal depths, life literally unfolds in perpetual slow motion. Enzymes operate at a snail's pace, nerve impulses fire at leisurely intervals, and the heart beats only a few times a minute. Now, if you cross this extreme, cold-induced deceleration of existence, with the monumental energy efficiency of Kleiber's law, a biological masterpiece is born. The result is an organism that requires virtually zero energy just to exist. It remains suspended in a state of permanent, masterful stillness. Scientists now believe this extreme efficiency is deeply connected to the very geometry of life itself, particularly the fascinating fractal nature of blood vessels and cellular delivery systems. Picture a giant California redwood tree. It has a massive trunk that branches out into thick limbs, then smaller branches, and finally into millions of tiny interconnected leaves. Our blood vessels work according to exactly the same principle. The larger an animal becomes, the more efficiently this delicate distribution network operates. It's as if nature has engineered a perfect fractal logistics system, one that becomes smoother and more effective at gigantic scales. But this evolutionary advantage has a dark flip side, because in the physics of the deep sea, nothing comes for free. The price for this incredible energy efficiency is the almost complete loss of speed and explosiveness. A deep-sea giant is no Porsche on the highway. It is a heavy freight train that struggles just to pull away. A colossal squid cannot plow through the waves like a dolphin, and it certainly cannot engage in long, high-speed chases. Its muscles are often softer, highly watery, and far less densely packed with mitochondria, the actual powerhouses of the cells. It is a glider, not a sprinter, and that single fact fundamentally changes the entire behavior of these creatures. Life in these abyssal depths is no relentless struggle. It is not a non-stop cycle of eat or be eaten, like the scenes we know from wildlife documentaries about the Serengeti. It is a long, almost ritualistic wait, a life of absolute patience, an existence where you move as little as humanly possible just to avoid wasting the precious store of energy you absorbed with your very last rare bite, maybe 3 months ago. Think of the anglerfish or the giant jellies of the deep. They don't hunt, they don't actively swim around looking for prey. Instead, they suspend themselves in the deep black like living, silent traps. They let the prey come to them. This strategy of the ultimate ambush predator is the direct, uncompromising consequence of their metabolism. In this realm, the rule is simple. Move, and you lose. Wait, and you win. Perhaps. It is the most extreme empire of maximum austerity. Imagine you had to make a single tank of gas in your car last for an entire year. You wouldn't drive around just for fun ever again. You would only start the engine when it was absolutely vital. You would coast down every single hill in neutral. And that is exactly what these creatures do. They utilize the ocean currents, they exploit their own buoyancy, and they use their sheer size to glide elegantly through time, rather than bitterly fighting against it. An engine that permanently runs at the lowest possible RPM experiences virtually zero wear and tear. In the abyssal depths, the biological clock ticks by its own entirely unique rules. While small, hyperactive animals at the surface often burn out. After just a few years, these deep-sea creatures can endure for centuries. Here, generations last for decades. It's as if someone pressed the pause button on life, but didn't push it all the way down. So, we now understand that the engine of these giants is incredibly efficient, requiring next to no fuel in the form of food. We know that the cold acts as a cosmic brake, throttling all biochemical processes down to a bare minimum. But this inevitably raises the next, much bigger question. How do you mate? How do you hunt? And how do you survive in a world that never sleeps, yet barely moves, and that it slows everything down and minimizes consumption? But every engine, no matter how efficiently it is engineered or how little fuel it ultimately uses, requires a second, unforgiving component just to function. Air. Without oxygen, there is no combustion, no energy conversion, and no life. And this is exactly where we face the next great puzzle, because a body that massive consists of billions of cells, and every single one of those cells is screaming for oxygen. In warm waters, this would be an absolutely unsolvable logistical nightmare. These massive creatures would quite literally suffocate from the inside out, because oxygen could never be transported fast enough into the deepest layers of tissue. But in the icy polar seas and the abyssal depths, nature has found a stunning way out of this evolutionary dead end. This is the ultimate key that allows sea spiders to develop stilt-like legs and enables giant isopods to grow into true monsters of the deep. It is the very substance that makes this seemingly impossible growth physically allowed in the first place. But where do these giants actually draw their breath from in the eternal darkness? The answer leads us straight to an invisible elixir created by the extreme cold itself. To truly understand why animals down there grow into such giants, we need to take a quick look into their physical kitchen. Imagine opening a bottle of carbonated mineral water. If that bottle has been sitting in the blazing sun all day and is warm, a miniature explosion happens the moment you twist the cap. The gas hisses out violently, and the water foams over uncontrollably. Why is that? Because warm water is incredibly poor at holding on to gases. The gas simply wants out. Now, by contrast, take a bottle straight from the fridge, ice cold, just above freezing. When you open it, you only hear a minimal, subtle hiss. The gas remains peacefully dissolved in the water. And that is exactly the great secret of our oceans. Cold water is physically capable of binding astronomically more oxygen than warm water. And in the waters around Antarctica, where temperatures often drop well below freezing, and the water only remains liquid, due to its intensely high salinity, the oxygen concentration is staggeringly high. The ocean there is no ordinary body of water. It is a downright oxygen-saturated soup, a true land of plenty for every single organism that exists within it. For us humans, this plays no role in daily life, as we famously draw our oxygen straight from the air. But for those marine creatures that must filter their life, sustaining oxygen directly from the water, this richness is the difference between scarcity and total abundance. And no one exploits this surplus as astonishingly as the sea spiders, the Pycnogonida. Perhaps you have seen a cellar spider sitting in the corner of your bathroom or basement. Those fragile, ghostly creatures with their incredibly long, thin legs and a tiny, almost non-existent body. A normal sea spider, like the ones found in a warm coral reef or the North Sea, looks similar but is tiny, often measuring only a few millimeters or a centimeter or two. You would easily overlook it. They appear to be little more than an insignificant speck on a stone. But when we dive into the Southern Ocean, we encounter their relatives, which could be straight out of a nightmare. Down here, these same animals, genetically almost identical to their tiny cousins, grow to monstrous proportions. Antarctic sea spiders reach leg spans of over 50 centimeters. Some specimens even up to 70 centimeters. That is significantly larger than the steering wheel of your car. Imagine a spider that, if it were to land on your face, would reach far past your ears. So why does nature play such a game? Why is it that in the icy silence of the poles, these creatures grow into such monsters? The answer lies hidden in their anatomy and in the physics of oxygen. Sea spiders are profoundly strange creatures. They essentially have no body. They consist almost entirely of legs. Their torso is so tiny that their internal organs, their stomach, even their reproductive organs, had to be outsourced into their legs. And most importantly, they have neither lungs nor gills. These animals breathe through simple diffusion. They absorb oxygen quite literally straight through their skin. The oxygen from the water must penetrate directly through their hard outer skin into their tissue. It is an extremely inefficient process. Physically speaking, diffusion sets a ruthless limit on growth. As an animal gets larger, the volume that needs to be supplied increases dramatically. But the surface area, the skin through which the life-sustaining oxygen enters, simply does not grow at the same rate. Eventually, a tipping point is reached where the interior tissue simply starves. It's the classic surface area to volume ratio, a mathematical law that gives every biology student a headache. In warm waters, this biological threshold is reached incredibly fast. If a sea spider in one of our local lakes were to grow as large as a dinner plate in midsummer, it would quite literally suffocate from the inside out. The oxygen simply couldn't penetrate through the skin fast enough to reach the deep-seated cells in the center of the legs. The animal would die, long before it even reached maturity. It is a relentless physical dead end, but right here, at this breaking point, nature suspends the rules. Because in the Antarctic ice, a transformation begins that defies every textbook in biology. But in the polar seas, the laws are different. Here, that invisible oxygen barrier is simply broken. Because the water in the Antarctic stores such an incredible amount of oxygen, the pressure with which this life-sustaining gas is literally forced into the animal's body is massively higher. Oxygen diffuses deeper, faster, and much more efficiently into the tissue, all the way down into the smallest corner of their massive legs. The physical limit that normally traps these animals in their small size is suddenly lifted. Evolution is like a gas pedal. As soon as the resistance, in this case, the lack of oxygen, disappears, it pushes that pedal all the way to the floor. In the harsh, freezing cold of the Antarctic, there is no brake left. And so, nature was able to transform an inconspicuous, tiny spider-like creature into a true monster, one that can exist solely thanks to the pure physics of the cold. Since the limiting factor of oxygen deficiency simply vanishes in the depths of the Southern Ocean, these spiders were able to grow larger and larger over millions of years. There was no physical wall to stop them. At the same time, their extreme energy-saving mode, that slow metabolism we discussed earlier, helps them keep oxygen demand to an absolute minimum. It is the perfect evolutionary combination. A massive supply of oxygen meets a minimal demand. The result? Spiders with leg spans rivaling the size of small dogs. This phenomenon is what we call polar gigantism. It differs fundamentally from classic deep-sea gigantism, even though both worlds often overlap. While in the deep sea, immense pressure and extreme food scarcity are typically the drivers of growth. In the polar regions, it is primarily the interplay of cold and oxygen. The colossal squid we encountered earlier is a true double winner here. It benefits from both worlds. But the sea spiders, they are the true children of the icy cold. But what do these giants actually do with their gigantic stilts all day? They are not fast hunters. Remember the energy-saving mode. Giants move with a ghostly, deliberate slowness across the seafloor. They use their long legs like delicate stilts, stepping effortlessly over obstacles, sponges and coral forests. They are not fighters. They are the vacuum cleaners of the deep. Their most important tool, a specialized snout known as the proboscis. With this proboscis, they pierce their prey, usually soft organisms like sea anemones or hydroids, sometimes even starfish. Then they calmly suck out their bodily fluids, much like someone sipping a strawberry milkshake through a straw. For the prey, it is a cruel and inexorable process, but for the spider, it is the most highly efficient way to obtain precious nutrients in this inhospitable wasteland. But the prey itself is anything but ordinary down here. The starfish being targeted by these spiders are themselves truly gigantic. Some Antarctic species do not have the familiar 5 arms we know from our beach holidays, but up to 50, reaching truly massive proportions. It is a clash of titans in slow motion. A giant starfish against a giant sea spider in a world so mercilessly cold that every single movement takes an eternity. Another aspect makes this oxygen surplus so fascinating. It does not merely allow these animals to grow to gigantic sizes, it also enables them to develop structures that would otherwise be far too costly to maintain. Biology is always a matter of budgeting. Organisms with limited oxygen must build sparingly. But beneath the Antarctic ice, the budget is so abundant that evolution can afford a true luxury. Structures that extend far beyond any physiological necessity. A large body retains heat more effectively, or, more precisely, it cools down more slowly and remains thermally stable despite even the slightest environmental fluctuations. This is the famous Bergmann's rule. Although it is most commonly discussed in the context of warm-blooded animals, its underlying principles cast a long shadow here as well. But let us pause for a moment. We now understand why these creatures can grow large, and why, in many ways, they are driven to do so. The pieces of the puzzle are beginning to fall into place. But there is one more dimension, often forgotten in our fast-paced world. Time, a giant does not emerge overnight. A woodlouse in your garden may live for only a year or 2. A cellar spider in your bathroom rarely survives longer than 3. But the giants of the Antarctic play by entirely different rules. In this eternal cold, life seems to have lost its fast-forward button. They grow slowly, they age slowly, and they live, at least by our standards, almost in slow motion. In the freezing waters of the polar seas, time itself appears to obey different laws. Everything here is immersed in an extraordinary slowness. Growth, movement, reproduction, the entire rhythm of life. But there is one animal that takes this strange relationship with time to the absolute extreme. A vertebrate that was already swimming through the oceans when emperors and kings still ruled much of Europe, and when the streets of great cities were illuminated by lamps fueled with whale oil. We are now leaving the world of invertebrate giants and turning to the true master of time, the Greenland shark. A shark that moves through the water so slowly it often appears almost motionless. And yet it lives longer than any other vertebrate known to science. Prepare yourself for an encounter with living history. For us humans, time seems rigid and relentless. We measure our lives in seconds, hours, and years. We celebrate milestone birthdays, worry about every gray hair, and pursue the dream of eternal youth with tireless determination. A human lifespan of 80 or 90 years feels long, filled with triumphs and failures, crises and moments of joy. Entire generations come and go within that span, but when we turn our gaze northward, toward the icy, lightless waters of the Arctic and the North Atlantic, our human definition of old age begins to lose all meaning. Out here, in the eternal cold, a 90-year life is little more than the blink of an eye. Down there, at depths of up to 2,000 meters, where the water hovers between 2 and 7 degrees Celsius, a shadow glides through the eternal darkness. It moves so astonishingly slowly that, at first glance, it seems almost motionless. This is not a predator driven by bursts of speed, not like the great white sharks made famous by Hollywood. This shark is the very opposite of haste, a gray, scarred colossus. It resembles a drifting boulder more than a fish. This is the Greenland shark, also known as the sleeper shark. The Methuselah of the seas, the undisputed master of time. But to truly understand how old these creatures can become, we must first embark on a journey through history. For a moment, we must silence the ticking clock of our own world. Imagine standing before Cologne Cathedral. This monumental structure took more than 6 centuries to complete, stone by stone, generation by generation. Now imagine a shark swimming through the icy depths of the North Atlantic. While we stand here today, there may be Greenland sharks still alive that were born when the 30 Years' War was beginning to engulf Europe in fire and devastation. Empires have risen and fallen. Nations have been founded. Entire generations have lived and died. And throughout all those centuries, this single animal may have done little more than continue its slow, silent journey through the darkness of the deep, a silent witness from an age that feels almost unreachable to us today. Scientific studies have now revealed just how extraordinary these animals are. Greenland sharks are known to reach ages of at least 272 years, while the largest individuals may exceed 500 years. That makes the Greenland shark not merely a biological curiosity, but the oldest known vertebrate on Earth. While we search endlessly for the secret of longevity, this animal appears to have discovered a different strategy altogether. A life lived at an almost unimaginable pace of slowness. Some of the oldest sharks alive today may already have been swimming through the North Atlantic when Christopher Columbus reached the Americas. They may have been alive when Michelangelo painted the ceiling of the Sistine Chapel. They may have witnessed an era in which the Aztec and Inca civilizations still flourished, long before the arrival of the Spanish conquistadors transformed an entire continent. The Greenland shark is not a living fossil. It is something far rarer. A living archive of history, carrying the memory of centuries within a body that has drifted silently through the darkness of the deep while the human world changed beyond recognition. But how is this possible? How can an animal made of flesh and blood, subject to the same fundamental biological laws as every other vertebrate, postpone the effects of aging for centuries? The answer lies in a remarkable combination of environment and physiology. The Greenland shark has turned a principle that many people in our fast-paced world rarely experience, extreme deceleration, into a highly successful survival strategy. It is not slow because it is weak. It is slow because, in its world, survival does not favor the fastest. It favors those that endure. In the near-freezing waters of the Arctic and North Atlantic, virtually every biological process unfolds at an extraordinarily reduced pace. Its heart beats only a few times per minute. It cruises through the darkness at speeds that often barely exceed a kilometer per hour. Its metabolism is so slow that its energy requirements are astonishingly low. In many ways, the Greenland shark functions like a living system suspended in slow motion. The cold acts as a natural preservative. Chemical reactions proceed more slowly, cellular wear accumulates more gradually, and the machinery of life operates at a pace that seems almost unimaginable from a human perspective. Growth slows down. Aging slows down. Even the processes that ultimately lead to death appear to be stretched across centuries. Yet this life in slow motion comes with extraordinary consequences. Consider our own species. Humans typically reach sexual maturity during their teenage years, often around the age of 13 or 14. For the Greenland shark, however, adulthood arrives on an entirely different timescale. Current estimates suggest that these sharks do not reach sexual maturity until they are around 150 years old. By the time a Greenland shark is finally ready to reproduce, entire civilizations may have changed, and 5 or 6 human generations may already have come and gone. For this ancient inhabitant of the deep, what we consider a lifetime is merely the beginning of adulthood. Take a moment to consider what this truly means. A Greenland shark must survive for roughly a century and a half before it can even begin to reproduce. For 150 years, it must endure the hazards of the ocean, evade predators, navigate a changing environment, and increasingly, avoid the dangers posed by human activity. Its youth lasts longer than 2 complete human lifetimes. And it is precisely this extraordinary biological patience that makes the Greenland shark so vulnerable. In a rapidly changing world, shaped by industrial fishing, climate change, and human expansion, a strategy built on extreme slowness can become a dangerous disadvantage. When a mature Greenland shark dies, the loss extends far beyond that of a single animal. What disappears is the product of more than a century of growth and survival. An investment of time on a scale rarely seen anywhere else in the animal kingdom. Yet this remarkable lifespan raises an obvious question. How do we actually know any of this? After all, sharks do not carry identification cards, and no one can ask them when they were born. For decades, scientists faced a seemingly impossible challenge. Most fish reveal their age through growth rings in bones or other hard structures, much like the rings of a tree. But the Greenland shark refused to cooperate. It seemed to age so slowly that conventional methods offered few reliable answers. So how do you determine the age of a creature for which an entire human lifetime represents only a fraction of its existence? To solve that mystery, researchers had to look somewhere no one had looked before, into the very eyes of the shark itself. Unlike many bony fish, which record their age through annual growth rings in tiny structures known as otoliths, much like the rings of an ancient tree, sharks offer no such convenient record. Their skeletons are made of cartilage rather than bone, leaving scientists without one of the most important tools traditionally used to determine age. For decades, the Greenland shark remained an enigma. Then, researchers discovered an answer in one of the most unlikely places imaginable. The shark's eye deep within the lens are specialized proteins that form during the animal's earliest stages of development, while it is still an embryo. Once created, these proteins become locked in place. In a sense, they form a biological archive, a record established before birth and preserved throughout the shark's entire life. What makes these proteins so valuable is that they are metabolically inert. Unlike most tissues in the body, they are neither replaced nor renewed. The organism leaves them untouched, preserving them for centuries within the transparent core of the lens. They are, in effect, a sealed time capsule. As the shark grows, new layers are gradually added around this original center, much like the layers of an onion accumulating over time, and therein lies the secret. At the very heart of the lens lies material that has existed since the shark's earliest beginnings. Reach that tiny central core, and you are holding something remarkably close to the animal's biological birth certificate. For the first time, scientists had found a way to look directly into the distant past of a creature that seemed to live outside the normal boundaries of time itself. By extracting the innermost core of the eye lens and subjecting it to radiocarbon analysis, researchers were able to estimate when these proteins had originally formed. To achieve this, they made use of an unexpected marker from one of the most turbulent chapters of modern human history, the atmospheric nuclear tests conducted during the 1950s and 1960s. These explosions released large quantities of radioactive carbon into the atmosphere. Over time, this carbon spread throughout the oceans, leaving behind a distinctive chemical signature, an invisible timestamp embedded within marine ecosystems around the globe. Any animal growing during this period incorporated this unique radioactive fingerprint into its tissues. For scientists, this so-called bomb pulse became an invaluable chronological marker. If the proteins at the center of a shark's eye lens lacked this characteristic signature, the animal must have been born before the nuclear age, before humanity had left this unmistakable imprint on the planet. Using sophisticated radiocarbon measurements and statistical models, researchers were finally able to estimate the age of some of the largest Greenland sharks ever examined. The results were astonishing. One female, measuring roughly 5 meters in length, was estimated to be at least 272 years old. Depending on the model used, her true age could have been considerably greater, perhaps even exceeding 4 centuries. If those estimates are correct, this animal may have begun its life at a time when the Renaissance was still reshaping Europe and large parts of the modern world had yet to be explored by Europeans. At that point, we are no longer looking at an animal in the ordinary sense. We are looking at a biological monument, an organism that has endured through centuries of human history while continuing its slow and silent journey through the darkness of the deep. When we observe this ancient wanderer, another remarkable detail immediately draws attention. Something both fascinating and slightly unsettling. Many Greenland sharks possess cloudy, milky eyes that give them an almost ghostly appearance, as though they have emerged from another age. The cause is often a tiny parasitic copepod known as Omatocoita elongata. This small crustacean attaches itself to the shark's cornea, where it may remain for years. Suspended from the eye like an unwelcome passenger, it feeds on surface tissues and can severely impair the shark's vision. In some individuals, the damage is so extensive that sight may be greatly reduced or even lost altogether. For humans, the idea is difficult to imagine. The thought of carrying a parasite attached to one's eye would be the source of constant discomfort and anxiety. In the lightless depths of the Arctic Ocean, where eternal darkness reigns, eyesight is of limited value. The Greenland shark does not depend primarily on vision. Instead, it perceives its surroundings through an acute sense of smell and highly developed sensory systems capable of detecting subtle signals in the water around it. For many years, researchers speculated that the copepod attached to the shark's eye might even be bioluminescent, potentially attracting prey toward its host. A bizarre and seemingly ingenious partnership. Today, however, that hypothesis is considered unlikely. The Greenland shark has little need for light. It moves through a world where darkness is the norm, navigating the deep through senses far older and more reliable than sight. And so the parasite remains little more than a passenger. The shark cannot easily remove it, nor does it appear to gain any benefit from its presence. It simply endures the intrusion, continuing its slow passage through the cold abyss as it has for centuries, a nearly blind giant, an animal of extraordinary age, a predator moving so slowly that it seems almost detached from the frantic pace of life itself. Yet this raises an obvious question. How can such a creature survive in the unforgiving wilderness of the North Atlantic? What does a predator eat when it swims so slowly that even many of its potential prey could easily outpace it? The answer reveals perhaps the most remarkable aspect of the Greenland shark. It does not survive through speed. It survives through patience. The Greenland shark is not a specialized hunter pursuing prey in explosive bursts of energy. It is an opportunist, an ancient inhabitant of the deep that has learned a simple lesson over centuries of existence. In the cold darkness of the Arctic, time is often the most powerful advantage of all. He eats whatever drifts into his path. In the stomachs of Greenland sharks, researchers have found fish and squid, exactly what one would expect. But they have also discovered things that seem completely out of place. The remains of reindeer, horses, and even more astonishingly, polar bears. A polar bear. How does a nearly blind, incredibly slow shark catch one of the Arctic's most powerful predators? The answer is as simple as it is surprising. In most cases, it probably doesn't. The Greenland shark is one of the great scavengers of the Arctic. Guided by an extraordinary sense of smell, it locates carcasses that sink into the depths or drift beneath the ice. In the cold waters of the North Atlantic and Arctic Ocean, where food can be scarce and decomposition is slow, almost nothing goes to waste. When a polar bear dies and disappears beneath the freezing waves, the Greenland shark may eventually arrive. When a reindeer ventures onto unstable ice, or the carcass of a large animal is carried out to sea by rivers and currents, the shark is ready to take advantage of the opportunity. Some researchers even suspect that Greenland sharks occasionally prey on sleeping or unsuspecting seals. But whether scavenger or hunter, the principle remains the same. Conserve energy whenever possible, and let patience do the work. He is the ultimate scavenger of the Arctic, a silent shadow that maintains the balance. You could call him the vulture of the deep, a creature that does not need to kill because he has integrated death into his strategy. While we humans view death as an ending, for him it is simply another nutritious stage in his centuries-long journey. With a length of up to 7 meters and a weight of 1,400 kilograms, he is a colossal reservoir. A single large meal can provide enough energy to sustain him for months. His immense body and extraordinarily slow metabolism allow him to process that energy at a pace that seems almost unimaginable to us. He doesn't need to hunt constantly. He doesn't need to rush. He only needs to be present when opportunity appears. His sheer size and remarkable energy efficiency have turned patience into a successful survival strategy. While most predators depend on frequent meals and relentless activity, the Greenland shark can afford to wait. In the darkness of the deep, time works in his favor. He does not rely on the fast chase. He does not need to sprint. He only needs to be there when death at the surface claims its bounty and lets it slowly sink down into his realm. He is the scavenger of the North Atlantic. But this title doesn't do him justice. He is a guardian of majestic significance. He cleanses the ocean, taking in death and transforming it into something unique, a life so incredibly extended that it shatters our human concepts of time. This dependence on dead biomass, on the remnants drifting down from the world of light, is not only essential for the Greenland shark. It is the fundamental principle of the entire deep sea. While the shark secures the big chunks, the wayward polar bear, or the dead reindeer, the rest of the deep sea community waits for something much finer, something omnipresent. We mentioned a term earlier that sounds almost poetic, yet serves as the lifeline for an entire planet: marine snow. But what exactly is it? And what happens when instead of a single reindeer, the largest organism on the planet dies and lands on the seafloor, creating an enormous feast for an entire city of deep-sea creatures? This leads us to the most spectacular food source the eternal darkness has to offer. The whale fall. When a giant of the seas dies, its story does not truly end. Instead, a completely new chapter begins. A single carcass can sustain an entire ecosystem for decades. The death of such a giant secures the survival of thousands and proves, beyond a doubt, that in the deep sea, nothing is truly wasted. Everything that passes through the world above eventually becomes the foundation for a new beginning below. And while we, in the world of light, often strive for permanence, the Greenland shark has long since found its own version of it. In the stoic patience of the eternal night, for now we leave him there, slowly feeding on his discovery. For a creature like this, life, however harsh and dark it may seem, eventually offers its rewards. In time, every meal becomes a feast, and perhaps that is the lesson hidden within a creature that can outlive generations of humans. The secret of survival lies not in speed, but in patience, not in the sprint, but in the waiting. Yet the Greenland shark is a special case. Large enough and mobile enough to track down those rare, gigantic food sources, it reigns as one of the deep sea's ultimate scavengers. But what about the countless others? What about the billions of small and medium-sized creatures that inhabit the seafloor, from the vast abyssal plains to the deepest and most hostile ocean trenches? How does an entire community survive when it cannot depend on the next great feast? The answer lies not in the large chunks of food that occasionally sink from above. Instead, it depends on something far more reliable, a steady and almost magical stream descending from the world of light. When you think about nutrition in the deep sea, you first have to let go of almost every assumption that comes from life at the surface. Above, in the sunlit waters, energy is abundant. Plants and algae convert sunlight into chemical energy. Small animals feed on algae, and larger animals feed on them in turn. It is a complex and constantly moving web of life, but below roughly 200 meters, the ocean begins to change. The light gradually fades, and with it, the possibility of photosynthesis. Anyone hoping to survive in these depths must adapt to a very different reality. Food is scarce, opportunities are unpredictable, and patience becomes one of the most valuable survival strategies of all. From depths of around 1,000 meters and beyond, eternal darkness takes over. No sunlight reaches these waters. Without sunlight, photosynthesis cannot occur, and without photosynthesis, there are no plants to form the foundation of a local food chain. In biological terms, the deep sea is a world with almost no internal food production. The creatures that live here are not producers but consumers, dependent on energy that originates far above them in the illuminated layers of the ocean. And that energy arrives in a surprisingly gentle form. Slowly and continuously, tiny particles drift downward through the darkness, carrying with them the remains of life from the surface world. For much of the deep sea, it is nothing less than a lifeline. This steady dependence on food from above forms the foundation of life throughout the deep sea. For the countless creatures that crawl, drift, and hunt in the darkness, there is no alternative source of energy. Everything ultimately depends on a constant rain of organic matter descending from the world above. Scientists have given this silent transfer of biomass a surprisingly poetic name: marine snow. The term sounds almost magical, perhaps even romantic. Yet, marine snow is made from the remains of life at the surface. Tiny fragments of plants, microscopic organisms, waste particles, and countless other traces of a living ocean slowly sinking into the depths. To picture it, imagine standing inside a vast Gothic cathedral in the middle of winter. Perhaps the soaring interior of the Ulm Minster, or the immense nave of Cologne Cathedral. The air is cold and still. Darkness fills the space above, and the vaulted ceiling seems impossibly distant. Then, from somewhere high overhead, tiny white flakes begin to drift downward. Slowly, silently, almost imperceptibly, they float through the darkness, gently swirling as they descend, before finally settling on the stone floor below. From the perspective of a creature living on the deep sea floor, this is not far from reality. Looking upward into the darkness, marine snow appears as an endless shower of tiny particles drifting down from a distant and unseen world. But unlike winter snow, these falling particles are not made of water. They are made of life. And for much of the deep ocean, they represent the difference between survival and starvation. But these flakes are not made of frozen water. They are the remains of life from the sunlit world above. Marine snow consists of dead plankton, the discarded shells of microscopic organisms, fragments of algae, and, quite simply, enormous amounts of biological waste. Every day, particles from fish, jellyfish, whales, and countless other creatures begin a slow descent into the darkness below. A journey that can take weeks or even months. What is little more than waste at the surface becomes a vital resource in the deep ocean. For many species living thousands of meters below, this constant rain of organic material is the foundation of survival, yet marine snow is far from a perfect source of energy. As each particle sinks through the water column, it passes through layer after layer of life. Bacteria begin breaking it down. Small animals feed on it. Midwater fish intercept the richest fragments. Again and again, the material is consumed, transformed, and recycled during its long journey downward. By the time it reaches the seafloor at depths of 4,000 or even 6,000 meters, only a small fraction of its original energy remains. What finally settles onto the abyssal plain is often little more than the last nutritional traces of a journey that began far above in the sunlight. And yet, for the deep sea, even these remnants are enough. Entire ecosystems survive on what the rest of the ocean has already used and left behind. In many ways, life in the deep sea depends on what remains after countless others have already taken their share. The creatures below survive on the nutritional traces of a feast that took place far above them in the sunlight. To make use of this scarce resource, some species have evolved remarkable adaptations. Among the most fascinating is the vampire squid, a mysterious inhabitant of the ocean's oxygen minimum zones. Despite its dramatic name, the vampire squid is no fearsome predator. It does not hunt large prey, nor does it feed on blood. Instead, it lives a surprisingly delicate existence, relying on the constant fall of marine snow. Extending from its body are two long, specialized filaments, unlike the arms of a typical squid. These sticky threads are released into the surrounding water, where they drift quietly through the falling particles. As marine snow settles through the darkness, the filaments collect tiny fragments of organic matter. The squid then carefully retrieves them, gathering enough material to sustain itself in an environment where every source of energy is precious. It is a life built on patience and efficiency, thriving in one of the most resource-poor habitats on Earth. Yet marine snow can only support so much life. It provides a steady trickle of energy, enough to sustain vast communities over time, but rarely enough to fuel dramatic growth or abundance. And then, on rare occasions, something extraordinary happens. A much larger source of food arrives from above. Something breaks through the darkness and transforms the seafloor below, turning a landscape of scarcity into one of sudden abundance. The gray monotony of the seafloor is shattered by an event as significant to the inhabitants of the deep as a great fortune would be to us. A whale dies. When a giant of the oceans, a blue whale, a fin whale, or a sperm whale, perishes at the surface and is not swept toward a coastline, its final journey begins. Its massive body, laden with tons of flesh, fat and bone, slowly sinks into the abyss. It is not merely a carcass, it is a falling continent of energy, one that will transform the eternal darkness for decades to come. This process is called a whale fall. When such a giant reaches the seafloor, it changes its surroundings almost instantly. Imagine standing in the middle of a desolate, arid desert that hasn't seen rain for centuries, and suddenly a fully stocked supermarket drops from the sky. A single whale fall brings as much concentrated energy to one location as would normally drift down as marine snow over 2,000 years. It is a biological time bomb that suddenly explodes, shattering the silence of the deep and transforming everything around it. What follows is comparable to a stampede at a free buffet grand opening or the rush for the best bargains at a winter sale. Only here, it isn't about material possessions. It is about pure survival. Shadows emerge from the darkness. Sharks, giant crabs, hagfish. An army of scavengers arriving from miles away. They sense the sudden abundance of energy that has reached the seafloor in a single stroke. It is a biological gold rush where not a single second can be wasted. It is pure chaos, yet it is organized chaos. First, the mobile giants arrive. Sharks, like our Greenland shark or the sleeper shark, hagfish, and massive bony fish. With surgical precision and raw force, they tear large chunks of flesh from the carcass. This process can take months, but once they are finally full and depart, the feast is far from over. On the contrary, a new phase is only just beginning. Now begins the hour of the invertebrates, the unsung heroes of this story, recycling every last gram of the giant back into the cycle of life. Giant isopods and amphipods swarm in from miles away. They possess a sense of smell so refined that they can detect the scent of decay in the infinite blackness like a beacon. And here, we see the true evolutionary advantage of their remarkable size in action. Do you remember the principle of storage? When a giant isopod arrives at a whale fall, there is no hesitation. It eats and eats. It is hardwired to store as much energy as possible within its armored body, because it knows that the next meal may not come for years. These animals possess the remarkable ability to stretch their bodies to the limit. An impressive anatomical feat. They eat themselves into a state that we might call a food coma after a lavish holiday feast, though here the term takes on an entirely different meaning. They consume such enormous quantities of food that they become almost completely immobilized. It is a state of total saturation, purchased at the cost of vulnerability. For days or even weeks, they may be barely able to move. It is a high-stakes strategy adopted by creatures that know the next opportunity for a meal may be a very long way off. Their legs barely touch the ground, so distended have their bodies become. They sacrifice their mobility, their primary means of defense, for this one vital store of calories. It sounds risky in a world where standing still often means death. But at a whale fall, a strange and temporary truce often prevails. Everyone is full, and when the carcass finally yields no more flesh, the next phase begins. The animals burrow into the surrounding sediment, entering a trance-like state as they live off the energy gathered from this single decisive feast. For months, and sometimes even years, that stored energy sustains them. In a very real sense, they transform the giant's flesh into their own lifespan. A giant isopod that has gorged itself on a whale can, in theory, survive for 5 years without taking another bite. Its body is no longer just an animal. It is a massive storage tank. But the deep sea is even more inventive than that. It has not only produced survivors that make the most of rare opportunities, it has also created specialists that turn what remains after the feast into a resource of their own. Researchers have discovered that some of these giants do not rely solely on whale-fall meat. In the most extreme corners of our planet, where pressures are immense and no ray of sunlight has touched the seafloor for millions of years, such as the Mariana Trench, scientists have found giant amphipods. These creatures have developed a completely different, almost uncanny ability. They have become masters of chemical extraction. They do not simply consume what they find. Instead, they are able to draw energy from materials that, to most other forms of life, would be little more than worthless waste. But these deep-sea amphipods have achieved the impossible. They have developed a unique enzyme, a specialized cellulase, that allows them to convert wood pulp directly into glucose, into vital sugar. This is a scientific sensation. In a world without plants, these animals have learned to harness the remnants of a completely alien world, the land. And even more astonishingly, the activity of this enzyme actually increases under extreme pressure. The deeper the trench, the more efficiently the amphipod digests. It is as if evolution has forged a tool that functions perfectly only where the pressure is at its absolute greatest. This ability to extract energy from almost anything, be it the dust of dead algae, the carcass of a whale, or an ancient tree trunk, is the key to survival. The giants of the deep are not picky gourmets. They are the planet's ultimate recyclers. Nothing is wasted. Every molecule of energy produced by the sun at the surface finds its way into the darkness sooner or later. Yet this extreme dependency, this silent link between the light above and the abyss below, makes the deep sea vulnerable. It is we who feed this stream, and it is we who have the power to destroy it. The deep sea ecosystem is not an isolated planet. It is the shadow of our own world. When we overfish the oceans, alter the climate, or disrupt plankton production, we are essentially turning off the tap for the giants below. Marine snow thins, whale falls become scarce, We have seen how these creatures fuel their massive bodies. We know they are opportunists. But in a world where food is so scarce, waiting is not enough. You must actively protect yourself or adapt your body to gain that crucial extra inch of reach in the darkness. This leads us to a creature that looks like a mechanical construct from a dystopian film, the Japanese spider crab. When we imagine extraterrestrial life, we often picture classics of science fiction. We think of the dark, machine-like visions of Metropolis, where towering constructs dominate the landscape. But we don't need to travel to Mars to experience this. We only need to dive off the coast of Japan. Deep, very deep. Let's change our perspective. Imagine you are a small fish foraging on the seafloor. Suddenly, pillars appear before you. Orange and white armored tubes that seem endless in the dim light. You look up and realize these aren't pillars, they are legs. Legs leading to a body hovering meters above you. The Japanese spider crab is the largest arthropod on our planet. When we speak of its size, we leave the realm of the biological and enter the realm of the physically impossible. A leg span of up to 4 meters. A classic VW Beetle could comfortably drive between its legs without even touching its body. Imagine a typical apartment with high ceilings. If you hung this crab on the wall, its legs would stretch from the floor to the ceiling and far beyond. It wouldn't fit in any trunk in the world. But why these bizarre proportions? Why is this animal 90% legs, with a body no larger than an armored fist? The answer lies in a brutal physical necessity: defense, reach, and survival in a world where a single misstep can mean death. Squid, large predatory fish, sharks, they all love to eat crab. Usually, the strategy is to hide, stay small, scurry under rocks, burrow into the sand. But in the vast openness of the deep sea, there are few places to hide. If you cannot hide, you must become a fortress. The Japanese spider crab is a living tank on stilts. Its exoskeleton is not just hard, it is a massive barrier. But its true defense is its sheer presence. A predator doesn't just have to crack the shell, it has to be able to overcome the beast itself. Who would voluntarily attack a 4-meter-wide monster of spikes? Its size is a deterrent. Most potential enemies living at these depths are simply too small to take on such a giant. It is the principle of liberation from predation. Because there is almost nothing that can eat it, evolution had a free hand to grow it even larger. The second factor is reach. Food in the deep is scarce and widely dispersed. Imagine sitting at your dining table, but your arms were 3 meters long. You could reach for the salt in the kitchen without ever getting up. That is exactly what the crab does. With its long sweeping claw arms, it scans a vast radius of the seafloor without having to move its heavy body. This saves precious energy. It pokes through the silt, grabs at carrion, algae, or mollusks, and brings them to its mouth slowly, almost mechanically. Its movements are not frantic. It strides slowly, deliberately, like a robot from another era. This deliberation has a physical reason often overlooked: the viscosity of water. At these depths, under immense pressure and frigid temperatures, water behaves differently. It feels thicker, almost syrupy. A small body would have to spend vast amounts of energy fighting this viscous mass. The spider crab, however, uses its length to its advantage. It doesn't glide, it stalks. It uses its long legs to overcome the water's resistance, moving efficiently over great distances. It is perfectly adapted to the fluid dynamics of the deep. Yet, despite its terrifying appearance and armor, there is a moment in this creature's life when it is as vulnerable as a newborn kitten. This moment is the price of gigantism. Like all crustaceans, it possesses an exoskeleton. But this armor does not grow with the animal. To grow, and it does so throughout its life, which can span up to 100 years, it must molt. Imagine wearing a suit of armor that has become too small for you. To take it off, you must painstakingly wiggle your soft body out of the rigid metal shell. For the giant spider crab, this is a logistical nightmare. It must pull its meter-long legs out of the old casing without getting stuck or tearing a limb. This process can take hours, and once it succeeds, it is soft. In culinary terms, it becomes a butter crab. For several days, until the new shell hardens in the seawater, this giant is completely defenseless. A 4-meter-wide puddle of jelly. During this time, it hides as best it can and prays that no ray or shark comes by. It is the only moment the king can be knocked from his throne. But once the shell hardens, it resumes its rule as a wandering reef, draped in sponges and life, drifting through the dark. They are not monsters. They are the peaceful gardeners of the abyss. They do not hunt, they clean. They transform death into new life. But despite their armor, the spider crab only lives in the attic of the deep. Now, we are going to the basement. We are descending to the foundation of the world, the Mariana Trench, the Challenger Deep. At nearly 11,000 meters, it is the deepest point of the Earth's crust, a place fewer people have visited than the Moon. To grasp this dimension, let's perform a thought experiment. Take Mount Everest, the highest peak on Earth, and drop it into this hole. It would disappear entirely, and its summit would still be 2 kilometers below the surface. But the true monster down here is not the darkness or the cold. It is the pressure. At 11,000 meters, the water column exerts a pressure of about 1,100 bar. An abstract number? Let's translate it into our reality. Imagine lying on the ground, and someone places the Berlin TV tower, concrete pillar and massive steel sphere included, directly onto your chest. That is the pressure raining down there. Or, to stick with the classic imagery, it is as if an elephant were standing on a postage stamp. When we humans dive into these depths in our best submersibles, we sit in spheres of solid titanium, with walls thicker than a bank vault, yet the metal groans under the strain. A single hairline fracture in a window would cause the water to jet in with such force that it would slice through everything inside like a laser beam before the entire vessel imploded in milliseconds. How can flesh, blood, and thin membranes exist where even hardened steel reaches its limit? The answer is surprisingly simple. These animals do not fight the pressure. They become one with it. We humans are so vulnerable because our bodies contain gas-filled cavities. Air is compressible. Under such pressure, a human lung would be crushed to the size of a pea in seconds, a horrific end. The inhabitants of the huddle zone, like the snailfish or the giant amphipod, have solved this problem by eliminating it. They possess no air-filled cavities, no swim bladders. Their bodies consist almost entirely of water and gelatinous tissue. And water is physically nearly incompressible. If you take a water-filled balloon into the deep, it hardly changes shape because the water inside builds up the same counterpressure as the water outside. These animals are not armored fortresses keeping the pressure out. They are open systems. The pressure passes through them. They do not feel the 1,100 bars as a burden, any more than we feel the atmospheric pressure currently resting on our shoulders. But that is only half the battle. The much greater problem occurs at the molecular level in the chemistry of life itself. Under extreme pressure, biological processes begin to fail. Proteins, the complex, 3D building blocks of life, depend on their specific shape. High pressure forces these proteins to deform or unfold. It is like trying to build a complex Lego tower while someone is constantly stepping on your hands. Enzymes stop working, and cell membranes turn rigid like butter in a freezer. By all logic, no cell should function here. Yet, Evolution has found a chemical trick, an antidote to the pressure. Researchers have discovered extremely high concentrations of so-called piezolites in the cells of these hadal creatures. The most well-known is TMAO, trimethylamine N-oxide. This molecule acts like a chemical scaffolding. It binds to water molecules, forcing them into a structure that helps proteins maintain their shape, even when the ocean tries to crush them. There is a direct linear correlation. The deeper a fish lives, the more TMAO it has in its cells. And here is a curious everyday fact. When TMAO breaks down, it forms trimethylamine, which is precisely the substance that makes old fish smell so fishy. Thus, the characteristic odor of marine fish is, in fact, evidence of their struggle against osmotic pressure and depth. The deepest fish in the world are literally pumped full of this stuff. Scientists even believe there is a theoretical limit to how deep a fish can live. At about 8,200 meters, the necessary concentration of TMAO would be so high that the fish's internal environment would be saltier than the seawater itself. Osmosis would reverse, and the fish would theoretically swell and burst. This is why, in the deepest parts of the Mariana Trench, at 11,000 meters, we likely won't find fish anymore, but only invertebrates like crustaceans and sea cucumbers that use different biochemical tricks. A prime example of life at the edge of the possible is Pseudoliparis swirae, the Mariana snailfish. Forget everything you know about monsters. This fish doesn't look like a beast. It looks like a pale, pink tadpole fillet. It has no scales, and its skin is translucent, with its liver shimmering through its abdomen. It seems fragile, almost cute. Yet, this small, soft fish survives conditions that would put the best steel-hulled submersible to the test. Deeper still, in the mud of the Challenger Deep, we find the giant amphipod Hirondelia gigas. It reminds us that pressure is not just an enemy, it can be a tool. Scientists found that its wood-digesting enzyme doesn't work worse under high pressure. It works better. It responds to the pressure. The higher the pressure, the more efficiently it breaks down cellulose. When we bring them to the surface, into our comfortable atmospheric pressure, they die not just because they pop, but because their internal chemistry fails. They freeze from the warmth and suffocate from the lack of pressure. Due to extreme pressure and frigid temperatures, water molecules behave differently. The water becomes thicker. For small organisms, it feels like swimming through liquid honey. This is a key reason why many deep-sea creatures grow larger. A massive body has more power and momentum to glide efficiently through this viscous medium. While a tiny bacterium down here struggles to move, size becomes a hydrodynamic advantage. When we look around in this crushing darkness, we notice something. Many of these creatures look as if they come from another era, primitive, simple, almost primordial. And that is no coincidence. The Mariana Trench and the deep ocean plains are places of absolute stability. While continents drift, ice ages come and go, meteorites strike, and civilizations rise and fall on the surface, everything down here remains the same. Cold, dark, under pressure, this eternal consistency has a fascinating effect on evolution. While evolution on land is often a frantic race, a constant need to adapt to new climates and new predators, down here it has taken its foot off the gas. Why change when the world around you has not shifted in 50 million years? We are looking through a window into the past. We are seeing creatures that seem frozen in time. But this very ancient stability, which shaped these giants, might today become their greatest undoing. When we think about evolution, we usually have the image of a frantic arms race in our minds. We see the savanna, the antelope that must become faster to outrun the cheetah, and the cheetah that must become even more explosive to avoid starving. We observe viruses that mutate within months to outsmart our immune systems. Evolution, to us, is change, adaptation, the constant drive for something new, fueled by the brutal echo of a world in flux. But when we leave the surface and dive into the eternal darkness of the deep sea, someone seems to have hit slow motion, or even the pause button. Different laws apply down here. Evolution here is not a frantic stockbroker reacting in a panic to every millisecond of market fluctuation. It is more like an archivist in a quiet, dusty cellar, turning a single page once every few centuries. Many of the creatures we find down here, the giant isopods, the ancient sharks, are what we call living fossils. If these animals were to step into a time machine and travel back 100 million years, to an era when dinosaurs roamed the forests and the Alps hadn't even been formed, they would hardly be surprised. In the deep sea, they would find ancestors almost identical to the creatures we admire in the darkness today. A Tyrannosaurus rex would not recognize today's world. A giant isopod, however, might only wonder why the water tastes a bit different. But why is that? Why does time stand still in the deep? The first reason is the extreme stability of the habitat. On the surface, life is constant, often violent chaos. Ice ages come and go, sea levels rise and fall, continents drift apart, and volcanoes alter the climate. To survive on the surface, you must be flexible. Adaptation is not a luxury there, it is a necessity, otherwise you go extinct. The deep sea, however, is arguably the most consistent place on our planet from a geological perspective. At 4,000 meters deep, there are no seasons. No summer, no winter, no storms, no droughts, no heat waves. For millions of years, the temperature has remained constant, just above freezing. The pressure is always crushingly the same. The darkness is absolute. Evolution is usually driven by crises. When the world changes, selective pressure arises, adapt or die. But if the environment never changes, there is no reason to adapt. The design of the giant isopod or the vampire squid worked 100 million years ago, and it still works perfectly today. It is the principle often cited in the best engineering. Never change a running system. Why should evolution waste precious energy to redesign an organism that is already perfectly fitted to its niche? In a world without change, innovation is not an advantage, but a risk. But it's not just the lack of necessity, it's the lack of possibility. We have learned that in the cold, all chemical reactions slow down. This doesn't just affect digestion or heart rate, but also the molecular processes of DNA. Mutations, the random errors in the genetic code that drive evolution, happen less frequently, and even when they do occur, it takes much longer for them to establish themselves within a population. Think about the generations. On the surface, insects multiply at a frantic pace. A fruit fly has great-grandchildren in just 2 weeks. This means evolution has hundreds of opportunities every year to experiment with new variants. In the deep sea, the clock ticks differently. Remember the Greenland shark that doesn't reach sexual maturity until it is 150 years old? If one generation spans 50 or 100 years, evolution simply has fewer chances to step in. A single evolutionary step that takes bacteria on the surface just days takes millennia down here. Biological time is frozen in the deep sea. This leads to a fascinating strategy that biologists call K-selection. In nature, there are 2 ways to ensure the survival of a species. Way A is the shotgun method. You produce thousands of offspring, but invest no energy in them, hoping that out of 5,000 eggs, 2 or 3 will make it. That is the path many surface fish take. The giants of the deep choose way B, quality over quantity. In such a stable yet nutrient-poor habitat, it is pointless to send thousands of babies into certain starvation. Instead, animals like the giant grenadier produce only a very few eggs, but these eggs are huge, packed with nutrients like a generous startup capital for life. You can compare it to an elite apprenticeship program. Instead of flooding the market with unskilled labor, you invest years into creating highly specialized experts. These children of the deep enter the world already large, strong, and developed. They have a much higher chance of survival. But this strategy requires calm. It requires a world that is predictable. Why invest a fortune into a single egg? Because in the deep sea, you have a guarantee found nowhere else. The certainty that tomorrow will look exactly like today. It is a biological contract with eternity. This slowness carries a profound philosophical weight. While a coral reef is a brutal war zone, where every square centimeter is contested, where corals poison and fish bite, the deep sea follows a different law. Here there is space. Population density is so incredibly low that you might not encounter your neighbor for kilometers. Why develop a complex arsenal of weapons or defense strategies when the nearest rival lives 3 kilometers away in the dark? Many deep-sea creatures have lost their aggression or never developed it at all. They live in a peaceful coexistence, dictated by scarcity. Are you fascinated by the idea of a world without time? A place where hurry isn't just a foreign word, but biologically meaningless. These giants are massive because they possessed the most precious resource on Earth: time. They are the product of an evolution that was never rushed. For millions of years, they were allowed to grow, to claim their niches, and to perfect their energy-saving mode, safe from faster predators, safe from climate catastrophes. They are specialists of absolute stability. But here lies the tragic trap. Specialization is a one-way street. Imagine an old master craftsman who has spent his life building the perfect wooden carriage wheels. He is a genius of his trade, until the automobile is invented. His perfection suddenly becomes useless, not because his work was poor, but because the world moved too fast around him. For 50 million years, the deep sea was a fortress of eternity. But today, in the Anthropocene, this bastion is beginning to crumble. We are altering the ocean's chemistry, heating its waters, sending plastic into the Mariana Trench. What happens when you take a system programmed for slow motion and deep cold and suddenly force it into fast forward? Animals that take centuries to adapt are now facing a world we are turning upside down in a matter of decades. The stability that once made these giants kings may now become their tomb. Because evolution has no turbodrive, the laws of nature do not accelerate just because we are in a hurry. Let us leave the biology behind and look at the threat creeping invisibly but relentlessly into the abyss. A threat that comes not with teeth or claws, but with molecules and degrees Celsius. It is a threat that does not come with teeth or claws, but through molecules and degrees Celsius. We have painted a picture of creatures that seem like invincible titans. We have admired the armored shell of the giant isopod, resembling a military vehicle. We have trembled before the rotating hooks of the colossal squid, and we have marveled at the resilience of the Greenland shark. Enduring for centuries, it seems as though nothing could shake these rulers of the darkness. They have survived meteorite impacts that wiped out the dinosaurs. They have ignored the drifting of continents. They appear like rocks amidst the surf of Earth's history. But this impression is dangerously misleading. It is one of nature's most tragic ironies. The very factors that made these animals giants, the extreme stability, the cold, the oxygen abundance, are today their greatest weakness. Consider a high-precision mechanical watch, a masterpiece of craftsmanship. It is designed to run with millisecond accuracy under strictly defined conditions. an engineering marvel. But if you take this watch, built for a sterile, cool room, and place it in a sauna, the gears will expand, the oil will become too thin, and the springs will lose their tension. The entire system, however perfect it was, collapses because it lacks the tolerance for deviation. The giants of the deep are exactly such watches. They are specialized for a world that has not changed for millions of years. And now, within a geological blink of an eye, within mere decades of human industrial activity, we are radically altering the parameters of their habitat. The problem is not simply that the water is warming and the animals are sweeting. The problem is a lethal pincer movement playing two physiological mechanisms against each other. The first arm of this pincer is oxygen. Think of a bottle of carbonated water. Cold water traps gas. Warm water lets it escape. As the oceans warm, and they are warming down to terrifying depths, the oxygen content drops inevitably and physically. The foundation of their survival is beginning to evaporate. The oxygen-rich paradise that once enabled their gigantism is being stripped away, and this is where the trap snaps shut. The second arm of the pincer is metabolism. These animals are ectothermic. Their body temperature and metabolic rate are dictated by their environment. As the water warms, every chemical process in their cells accelerates. The engine that once hummed in an efficient idle suddenly begins to redline. The body demands more oxygen, but precisely when the warming water causes oxygen levels to plummet, the supply vanishes. It is as if you ordered a marathon runner to double their speed, while simultaneously pinching their windpipe shut. Scientists call this scenario the oxygen temperature scissors. The result is a chronic, merciless state of breathlessness. The consequences are already visible. Studies show that the body size of Antarctic sea spiders is already shrinking in warmed areas. The giants die first, not because they are weak, but because they are living at their physiological limit. A massive body with long limbs and thick layers of tissue simply has too far to transport oxygen. When levels drop, they suffocate within their own size. The situation is particularly tragic for our friend, the colossal squid. It is optimized to survive on just 45 calories a day. A master of energy efficiency. If temperatures rise, its metabolism is forced to accelerate. It suddenly burns energy it does not have. It would need to hunt to bridge the deficit, but it is a passive glider, not a predator. It falls into an energy deficit it cannot overcome. The result? The colossal squid might not go extinct, but it will shrink. It loses its majestic identity. The monster of legend becomes an ordinary, mid-sized squid, a tragic trivialization of a biological wonder. But it doesn't just affect the individual, it affects the foundation. The entire deep-sea ecosystem is designed like a house of cards. If we pull out the temperature card, everything begins to totter. If plankton currents shift due to surface warming, whale migration routes change. And if fewer whale carcasses reach the seafloor, the supply line for the deep-sea recyclers collapses. A silent death begins in the darkness, a collapse we won't even notice from the surface. If fewer whales die, or if their carcasses drift off course due to shifting currents, the supply line for the scavengers on the seafloor collapses. The giant isopods and hagfish wait in vain. A feast that should have lasted for decades never arrives, a devastating domino effect. But there is another, often overlooked crisis: ocean acidification. As we pump CO2 into the atmosphere, the ocean absorbs the brunt of it. The water turns more acidic. For creatures with calcified shells, crustaceans, mollusks, corals, building their protective armor becomes a struggle. In the deep, where immense pressure already makes building shell material a challenge, the rising acidity makes it existential. The armor of the giants could literally begin to dissolve, or the animals must expend energy they simply do not possess. Researchers warn that we may be heading toward a mass extinction in the deep sea. One we won't even notice because it happens so far away. We see the burning Amazon rainforest. We see the bleaching of Australia's coral reefs. But who sees the death of the amphipods in the Mariana Trench? It is a silent extinction. Imagine if St. Patrick's Cathedral were slowly crumbling to dust. But no one looked because it was hidden under a giant tarp. That is exactly what is happening to the biological cathedrals of the abyss. These animals are living relics. They carry genetic information millions of years old, forged since the Eocene. If they vanish, we don't just lose biomass, we lose the library of Earth's history. So, is there hope for the deep ocean giants? Life is resilient. Perhaps smaller, more adaptable species will take over the niches of the giants. Perhaps in 1,000 years, the deep sea will be populated by small, fast generalists, much like the rats and pigeons that have conquered our cities. Yet the era of these majestic, slow-moving giants, these dinosaurs of the abyss, could be coming to an end. The truly tragic irony is that these animals are no threat to us whatsoever. There is not a single documented case of a colossal squid ever harming a human. They live their lives in a world we can only enter if locked inside steel spheres. And yet, our influence reaches down to them. The exhaust from a car in Stuttgart or a coal power plant in China has direct physical consequences for a giant sea spider sitting 10,000 kilometers away, 4 kilometers deep in absolute darkness. We have seen that cold is the master key to gigantism. A blessing in terms of oxygen, but a curse in the face of climate change. But we have been blurring two concepts that must be scientifically separated: deep-sea gigantism and polar gigantism. Is a colossal squid really the same as a giant sea spider? Where exactly is the difference between deep and cold? It is time to bring order to this chaos. Let's stage a boxing match of ecosystems. In the left corner, deep-sea gigantism. In the right corner, polar gigantism. Let's start with the deep sea. Fundamentally, the deep sea is a place of poverty. Food is scarce. Here, gigantism is a strategy of scarcity, a desperate measure. Imagine a long-haul trucker driving a vast desert route where there is a gas station only every 1,000 kilometers. What does he do? He installs a massive auxiliary tank on his truck. He sacrifices speed and aesthetics for storage capacity. That is exactly what deep-sea gigantism is. These animals grow large to carry more energy reserves and to travel greater distances between sparse meals. A larger body is simply more efficient and endures longer. Pressure plays a supporting role, but the primary driver is hunger. The giants of the deep are essentially famine giants. They grew large so they wouldn't starve. Now, let's look to the right corner, the polar sea. Here, the situation is completely different. In the shallow waters around Antarctica, where light actually reaches the seafloor during summer, there is food. Plankton explodes, algae bloom. Hunger is not the primary problem here. Here, we encounter polar gigantism. Its driver is not scarcity, but pure luxury. Remember our oxygen theory? Icy water is a treasure chest overflowing with oxygen. Let's go back to our long-haul trucker. In the polar sea, the fuel, oxygen, is not just cheap. It's free and flows in abundance. Since there are no cost constraints, the driver doesn't build an economical truck. He builds a massive heavy-duty hauler, simply because he can. Antarctic sea spiders and giant polychaete worms are products of this abundance. Since oxygen sets no limits, they simply keep growing. At the same time, the cold slows their metabolism so significantly that they barely consume any energy to maintain their massive frames. The giants of the poles are luxury giants. They grew large because nothing held them back. So, who wins this comparison? Who produces the true giants? If we go by length alone, the polar sea often takes the lead. The lion's main jellyfish, Cyania capillata, is the living proof. Its tentacles can measure up to 37 meters. That's longer than a blue whale. Imagine standing on the Brooklyn Bridge and lowering a thread to the water below. That is the dimension of this creature. Compare that to its cousins in warmer waters, which barely reach the size of a dinner plate. Here, the cold has clearly forged a giant, buoyed by the density and oxygen content of the water. But when it comes to mass and sheer monstrosity, things get complicated, because the effects of deep and cold do not cancel each other out. They accumulate. The undisputed king of all invertebrates, the colossal squid, is the result of exactly this lethal combination. It lives in the icy Southern Ocean and simultaneously in the crushing depths. It is a case of combined gigantism. It benefits from the oxygen-rich cold and the energy efficiency of the deep. The result is a creature that weighs up to 700 kilograms, a living legend of flesh and mystery. This proves that when these two worlds collide, they produce titans that shatter our imagination. The fact that the colossal squid, weighing in at 500 to 700 kilograms, dwarfs the giant squid of temperate waters proves it. When the two factors of gigantism, extreme depth and freezing cold, unite, they create the true monsters of our planet. But let's look deeper. When we switch off the lights in America, it is never truly dark. Even in the deepest woods of Maine, or the dark winter nights of Montana, there is always ambient light. The moon, the stars, the distant glow of cities. We are creatures of light. For us, absolute darkness is a theoretical concept that we might only glimpse in a windowless basement when the fuse blows. Yet in the deep sea, from about 1,000 meters down, there reigns a darkness so complete it feels almost physical. No solar photons reach the seafloor here. By human logic, sight should be as redundant as sunglasses in a coal mine. Why invest energy in eyes if there is nothing to see? And yet, from this eternal night, eyes stare back at us that dwarf everything existing on the surface. The undisputed record holder is our old acquaintance, the colossal squid. Its eyes reach a diameter of up to 30 centimeters. Take a regulation basketball and hold it in front of your face. That is the sheer dimension of just one of this creature's eyes. They are the largest eyes in the entire animal kingdom. But why? Why does an animal living in a world of absolute pitch black develop optical instruments the size of a dinner plate? The answer leads us into a world that is not black, but filled with a cold, chemical fireworks display, bioluminescence. The deep sea is far from dead. It glows. Let's imagine a scenario. Imagine you are driving down a pitch-black highway at night. You turn off your headlights. At first, you see nothing. But then, slowly, you begin to perceive tiny points of light. The glow of a cigarette in the car ahead, the distant blink of a cell tower, the dim light of an instrument panel. In the deep sea, creatures communicate, hunt, and camouflage themselves using exactly this kind of light. The eyes of the colossal squid aren't meant for enjoying the view. They are high-precision light amplifiers. Scientists believe these massive eyes serve one critical purpose. They are a survival-critical early warning system. The only natural predator of an adult colossal squid is the sperm whale. When a whale dives into the depths, it is like a massive bus driving through a cloud of midges. Except here, the midges are tiny, bioluminescent plankton. When the whale plows through the water, it disturbs these organisms, and they flash in fright. Without realizing it, the whale pulls a glowing aura behind it, a halo of sparkling stardust. At 2,000 meters deep, a human eye would see absolutely nothing. But the colossal squid's massive eye, with its gargantuan pupil and ultra-sensitive retina, can detect this faint glimmer from hundreds of meters away. It doesn't see the whale itself. Instead, it sees the whale's shadow silhouetted against the stardust of the deep. That gives the squid the vital seconds it needs to escape, right before the whale's sonar can lock onto it. But light in the deep sea is a double-edged sword. To see is an advantage. To be seen is to die. This has fueled a fascinating evolutionary arms race, where camouflage is everything. And that is where color comes in. Have you ever wondered why so many deep-sea creatures, like the colossal squid or certain shrimp, are bright red? On the surface, a red animal would be as conspicuous as a fire truck, but water filters light. Red is the first color in the spectrum to be absorbed. Just a few meters down, it vanishes completely. In the deep sea, there is no red sunlight left to be reflected. Therefore, a red animal appears pitch black. It is the perfect cloak. But the colossal squid goes even further. Its reddish skin isn't just dark, it actively absorbs light. Much of its prey uses bioluminescence. If the squid were to grab a glowing creature, a pale body would reflect that light and immediately give its position away. Its reddish skin, however, absorbs every single bit of bioluminescent light that hits it. It remains a phantom. It is the stealth bomber of the abyss, absorbing light beams instead of reflecting them. Its reddish skin absorbs every bit of bioluminescent light that hits it. It remains a phantom. It is the stealth bomber of the abyss, absorbing light beams just as a radar-evading aircraft absorbs radio waves. But not everyone wants to hide. Some creatures use light as a lure. The famous anglerfish is the classic example. It carries a literal fishing rod in front of its jaws, ending in a glowing bulb filled with bioluminescent bacteria. In the absolute darkness, this tiny point of light is irresistible. Curious fish and crustaceans approach, thinking they've found a quick meal, but in a heartbeat, the trap snaps shut. It is a snare as simple and deadly as the witch's gingerbread house in Hansel and Gretel. However, there is one predator that has taken this light game to a level that can only be described as profoundly unfair. The dragonfish. To understand why, we must look at physics. Most deep-sea inhabitants produce blue or green light because those wavelengths travel furthest through water. Consequently, the eyes of deep-sea creatures have evolved to be extremely sensitive to blue and green, leaving them completely blind to the color red. This is where the dragonfish's superpower comes into play. It possesses a specialized light organ that emits a deep, crimson-red glow. It is a physically demanding feat, but tactically, it is absolute genius. It glides through the darkness as if carrying a stealthy red flashlight. While the dragonfish sees its prey, shrimp and small fish, brightly illuminated, they remain completely oblivious to the fact that they are being tracked. Their eyes are physiologically tuned only to the blue spectrum. For them, the crimson beam of the dragonfish simply does not exist. The dragonfish is a sniper with night vision goggles operating in a room full of blind people. It has secured a private visual channel, a secret frequency on which only it transmits and receives. This world reveals that the deep sea is far from empty. It is a high-stakes battlefield of information. Every flash, every glimmer can be the key to the next meal, or the final sentence of one's own life. Think of walking through a pitch-black forest at night, carrying a blazing lantern, a beautiful, warm light in the darkness. In the deep sea, carrying that lantern would be a fatal error. Whoever glows immediately gives away their position. This is why many animals have evolved complex mechanisms to control their light strategically. Some jellyfish, like the Atolla jellyfish, use light as a biological burglar alarm. When attacked, they begin to flash wildly and brightly, like a strobe light in a nightclub. The goal isn't to blind the attacker. It is a desperate cry for help. They aim to attract an even larger predator to consume their attacker. It is the perfect embodiment of the principle, the enemy of my enemy is my salvation. It is a risky gamble, screaming as loud as possible with light, hoping that the Godzilla of the deep appears and devours the attacker before they themselves are devoured. The vampire squid also masters this dark art. Instead of squirting ink, which would be completely useless in the absolute black, it releases a cloud of glowing slime. This luminous cloud confuses the attacker, perhaps even blinding them momentarily, while the vampire squid vanishes into the safety of the dark water. It is a biological flashbang made of pure light. We now see that the eyes of the giants and the lights of the abyss are inextricably linked. The colossal squid's massive eyes are no mere ornament. They are the direct evolutionary response to the faint glimmer of its foes. If it weren't for bioluminescence, these gigantic eyes would likely have atrophied long ago, much like those of blind cavefish hidden away in subterranean caverns. But evolution here didn't choose blindness, it chose supervision. Yet, sight is only one sense, and light is only a tool. In a world as extreme as the Mariana Trench or the Southern Ocean, having good eyes isn't nearly enough. You need strategies that encompass the entire body and the whole life cycle. We have seen how these giants eat, how they breathe, and how they see. But how do they behave? What does the daily life of an animal look like when it lives for 4 centuries and barely moves? Is laziness a deadly sin down here, or the highest virtue? It is time to look at the most extreme survival strategy of all. We must understand how to master a life that consists almost entirely of waiting, and why doing nothing can be the hardest work in the world. It is a lesson in patience that would test even the most stoic mind. In our world, we grow up with a proverb deeply embedded in our cultural DNA. Idle hands are the devil's workshop. Anyone who does nothing, who just lies around, is dismissed as unproductive. We admire hustle, non-stop activity, the bustling commutes of our city centers, or the chaotic rush of JFK Airport. To stand still is to regress. But if we were to pack this human work ethic into a submarine and send it 4,000 meters down, we would have to radically rewrite our entire philosophy. Down there, that constant drive to do something would be a swift death sentence. In the abyss, the golden law is simple. Idleness is the only way to stay alive. The biological machinery of these giants, their massive bodies, their huge eyes, their specialized enzymes, is completely useless without the right programming. And the operating system of these deep-sea creatures is set to a default mode that is incredibly hard for us to comprehend. Aggressive passivity. To understand just how extreme this strategy is, let's look at the daily routine of a typical deep-sea resident, like the colossal squid or a massive deep-sea anglerfish. Their lives consist of 99.9% absolute nothingness. A hunter sitting motionlessly in a tree stand in the woods of Pennsylvania for hours during autumn looks like a bundle of pure hyperactivity compared to these animals. A colossal squid doesn't actively swim around looking for prey. It drifts. It uses its neutral buoyancy to hang in the water column like a gargantuan balloon. Every movement of its tentacles, every single beat of its fins costs energy. And down here, energy is the hardest currency in the ocean. These creatures are not pursuit predators like a cheetah or a tuna. They are ambush predators of the most extreme kind. It's a high-stakes game of chicken. Whoever moves first loses precious fuel. Whoever waits might just win a meal. This radical strategy of sit-and-wait hunting is the real key to gigantism. Only because they don't move can they afford to grow so massive. A body that runs continuously on high gear like a sports car needs constant refueling. A body that functions like a parked warehouse requires almost nothing. But when the moment of truth arrives, when an unwary fish drifts within reach of those tentacles, everything changes. In milliseconds, the system switches from sleep mode to absolute explosion. The colossal squid fires its hook-lined feeding tentacles. The anglerfish snaps open its cavernous jaws, vacuuming the prey in with a sudden drop in pressure. It is a life of extremes, months of absolute silence, punctured by seconds of brutal violence. Do you have the patience of a deep-sea squid? Or do you already get restless when the microwave takes 2 minutes? This extreme patience demands a completely different adaptation toward food. We humans eat 3 meals a day. If we skip lunch, we get cranky. A deep-sea giant like the giant isopod has to deal with a very different reality. Permanent famine. Food down here doesn't arrive on a schedule. It comes in unpredictable waves. A whale carcass today, and then 5 years of absolute nothingness. To survive this, these animals have perfected the art of gluttony. When food is available, they don't eat until they are full. They eat until they are physically on the verge of bursting. We all know that heavy feeling after a massive Thanksgiving dinner at Grandma's house, when you can barely move. For the giant isopod, that is not an uncomfortable side effect. It is the ultimate evolutionary goal. They gorge themselves so much that their legs can barely touch the ground, severely limiting their mobility. They sacrifice movement for pure storage capacity. They become living pantries. This strategy allows them to endure periods of starvation that would kill any other creature. They don't starve. They endure. We have learned how these creatures utilize the light of bioluminescence and how they survive the immense pressure. We have come to understand that their perceived laziness is, in reality, their greatest evolutionary strength. But what does all of this mean for us? Why should we care about the fate of a giant isopod or a blind shark? Are they merely bizarre curiosities in a cabinet of natural wonders, or are they something more? It is time to ascend. But before we reach the surface, we must address one final, crucial question. We know their past, and we understand their present. But do these giants have a future at all? And what does their fate reveal about the state of our own planet? Let us piece together the puzzle. Let us look at the fragile equilibrium that holds this wondrous world together, and understand why we are wise to protect it with everything we have, even if we will never see it with our own eyes. We have traveled a long road. We descended from the sun-drenched surface into the twilight zone, traversed the eternal night, and finally touched the bottom of the Mariana Trench. We encountered creatures that defy our wildest nightmares and boldest dreams alike. We learned that isopods can grow to the size of soccer balls, and that colossal squids battle sperm whales deep in the dark using tentacles lined with rotating hooks. And we learned that some of these sharks were already swimming through these freezing oceans, long before the Mayflower ever set sail. Now, at the end of this expedition, we must resurface. We must decompress and return to our world of light, noise, and perpetual hustle. But before we crack open the hatch of our imaginary submarine and breathe in the fresh air, we must confront an uncomfortable truth. A truth that carries more crushing weight than the 1100 bars of water pressure down below. The truth is, we know next to nothing. It is an often repeated statistic, but that doesn't make it any less staggering. We have explored less than 5% of our oceans. We possess more detailed maps of the dusty surface of Mars than of the floor of our own seas. When we talk about the giants of the deep, about the colossal squid or the giant isopod, we are talking about tiny puzzle pieces we happen to find entirely by chance. Think of legendary explorers like Lewis and Clark forging into the uncharted American wilderness. They mapped what felt like a whole new world. But the deep sea is a cosmos that would have left even the most daring pioneers utterly speechless. Every single dive of a modern research submarine, whether operated by oceanographers from Woods Hole, Scripps, or international teams, brings new species to light. Every time we lower a camera into an unmapped fissure, we witness something no human eye has ever seen before. And that leaves open a fascinating, almost haunting question. What else is down there? If we have already discovered squids, as long as city buses and jellyfish, whose tentacles stretch past the length of a blue whale, is it really so far-fetched to believe that even greater things exist? We simply do not know if there is an upper biological limit to size. In a world so remarkably stable and unimaginably vast, entirely different titans could be lurking within the uncharted expanses of the abyssal plains. Perhaps not sea monsters that swallow ships, as the ancient sailor myths of the Kraken whispered, but biological wonders that would turn our entire understanding of life completely upside down. We humans are obsessed with finding extraterrestrial life on distant planets. We point gigantic radio telescopes into the deep cosmos. We send space probes to Jupiter's moon, Europa, hoping to find signs of life hidden within its ice-covered ocean. In doing so, we often forget that the true aliens are already here. They live right under our feet, or rather, beneath kilometers of water. These creatures strike us as visitors from a distant star. The Greenland shark, drifting blind and ancient through the icy sea. The giant crab, moving like a biomechanical machine. They prove to us that life does not play by a single rulebook. What holds true on land is completely worthless in the abyss. Life finds a way, even where we once deemed it utterly impossible. But this alien world is not nearly as isolated as we long believed. And this is the exact point where our admiration must shift into stark responsibility. We often view the deep sea as far away, out of sight, out of mind. But the oceans are a single, interconnected, pulsating system. What we do up here inevitably filters down. The warming waters and depleting oxygen of climate change were just the beginning. There are far more direct, brutal threats facing the abyss today. Plastic waste has already been discovered at the absolute bottom of the Mariana Trench, 11,000 meters down. The giants that have fed on marine snow for millennia are now consuming our microplastics. A giant isopod cannot distinguish between a natural nutrient and a toxic fragment of a degraded shopping bag. And now, an even greater danger looms, ironically triggered by our modern, supposedly green technology, deep-sea mining. Scattered across the vast abyssal plains lie manganese nodules, potato-sized lumps rich in rare metals. These are the exact raw materials required for electric vehicle batteries, smartphones, and wind turbines. Global industry is starved for these resources, but these nodules are far from dead rocks. They form the irreplaceable foundation and habitat for countless highly specialized organisms, growing layer by layer over millions of years. If we begin to plow through the ocean floor with multi-ton machinery, underwater versions of monstrous open-cast mining excavators, we will destroy, in a matter of hours, what took eons to create. We would erase entire ecosystems before we have even begun to understand them. The great, slow-moving giants of the deep would not stand a single chance. They cannot flee, and they cannot rapidly regenerate. A colossal squid or a Greenland shark simply cannot adapt to an industrial mining zone. Their strategy of slowness, which made them the undisputed rulers of the abyss across eons, would become their immediate death sentence. But why should we care? Why should a bank clerk on Wall Street or a school teacher in Pennsylvania care whether a giant isopod survives in the distant Pacific. First, because we are biologically dependent on them. The oceans are the lungs of our planet and Earth's greatest carbon sink. The creatures of the deep sea bind carbon from the surface and bury it within the eternal sediment. They play a vital role in the global climate system that we are only just beginning to grasp. If we destroy this massive, invisible gear train, it will trigger consequences for our climate that we simply cannot foresee. Second, and this is perhaps the more vital, philosophical reason, for the sake of the wonder itself. Who wants to live in a world stripped of all its mysteries? Who wants to live in a world where there are no monsters left, only extractable resources? The giants of the deep sea are the last great secret of our planet. They remind us that we do not control everything, we do not know everything, and we do not own everything. They are a mirror. When we look at the Greenland shark swimming alone through the Arctic darkness for 4 centuries, blinded by parasites upon its eyes, yet moving in absolute, unshakable tranquility, we see the ultimate countermodel to our own existence. We humans are frantic. We lose ourselves in a daily deluge of notifications and bad news. We drink coffee to fight fatigue, rush through stressful commutes, and get angry over traffic jams and internet comments. We live in a permanent fear of missing out. The shark has no fear of missing out. It is in no hurry. It simply exists. Perhaps in its blind, slow existence it is happier, or at least more peaceful, than we are in our hyper-optimized daily lives. Perhaps, deep down, we envy these creatures for their total detachment from time. The deep sea teaches us humility. It shows us that true greatness does not require volume. The quietest realm on Earth is simultaneously its most monumental. And it is entirely up to us whether these cathedrals of the deep continue to glow in the darkness, or vanish forever into the black. The true giants are quiet. They do not roar. They wait. They survived long before we ever placed the first stone upon another, but now it is entirely up to us. We are the first species in the history of this planet, with the power to either utterly destroy the deep sea or protect it forever. It is our choice, whether to plunder this untouched cosmos as an industrial quarry or preserve it as the holy grail of evolution. The monsters of ancient legends were always the animals, the kraken splintering ships, the sea serpent devouring sailors. But looking into the mirror today, we must confront a haunting question. Are we, perhaps, the true monsters? Are we the unpredictable force of nature that the colossal squid should fear, if it even knew we existed? The deep sea is resilient against time, but infinitely fragile against humanity. Its equilibrium is a finely tuned masterpiece of cold, pressure, oxygen, and eons of time. Remove just one component, and the entire system falls apart. We hope this journey into the abyss has permanently changed the way you look at our blue planet. The next time you stand on the shore and look out at the horizon, don't just see the waves. Remember what is happening kilometers beneath them. Remember that down there in the eternal darkness, a heartbeat exists, much slower than ours, but just as precious. Welcome back to the surface. The air up here is thin, the light is bright, but we are home. This was an expedition by the Terralog team. If you enjoyed this deep dive and want to keep unlocking the hidden wonders of our world with us, make sure to subscribe to the channel right now. What fascinated you the most on this journey? The biblical age of the Greenland shark, the sheer mass of the colossal squid, or the bizarre fact that deep-sea creatures can actually digest wood? Let me know in the comments below. I read every single one of them. Stay curious, and see you on the next dive.